Expressing solution concentration. We have qualitative terms, dilute and concentrated. And these are just relative. Dilute solution, small quantities of solute, concentrated, large quantity of solute. Those are somewhat useful. The quantitative measures are more useful. And there's a number of them. So here's a handy table from your book. So some of these we've talked about. Molarity is the amount of solute in moles divided by the volume in solution. The units are given over here. Molality is a little different. That's a lowercase m. Here we have amount of solute in moles per mass in kilograms, mass of solvent, not the solution. There's mole fraction, there's mole percent, and then there's parts by mass and parts by volume. But all of these have in common that you're relating some measure of quantity of solute to a quantity of solvent or solution. So molarity we've talked about before. This is an important one in chemistry. Moles of solute per liter of solution. That was back in section 4.4. The thing about molarity is that it decreases slightly. It changes slightly with temperature because the volume becomes slightly larger at higher temperatures. So in some situations, that is a problem because the molarity is changing and we don't need that. So to get around that, we use something called molality, which is so very similar in its name and its symbol to molarity that it just becomes very confusing for students, and I'm sorry. But the reason we deal with molality at all is it's independent of temperature. Here we're having amount of solute again in moles, but now we're looking at the mass of the solvent in kilograms, because the mass doesn't change with temperature. The volume does. Not much, but it can be enough to mess things up. So important to note, it's kilograms of solvent, not kilograms of solution. And molality and molarity are often similar in number if you calculate them for the same substance. What's the density of water? 1 gram per milliliter, right? What would the volume of 1 kilogram of water be? 1 liter. So 1 kilogram of water is 1 liter of water. So similar, but not the same. Okay? Like, couldn't they make it completely different? Sorry. There it is, molality. The symbol for that is a lowercase m. That's not on here. It was on the other one. Lowercase m. You got to be real careful with the lowercase m because it also means meter. So you kind of have to look at context. It's another reason I don't like it. Parts by mass and parts by volume. Chemists don't use these a lot, but they are used in many, many other professions that have to deal with concentrations. So parts by mass. We're just comparing mass of solute to mass of solution. The ratio of the mass of the solute to the mass of the solution, and we're going to multiply by a factor. So percent is per 100, right? So then we multiply the ratio by 100. So it's the ratio mass of solute to mass of solution. Because what is percent? It's parts, the part over the whole, right? So the part, the solute, divided by the whole thing times 100. Percent means per 100. This is also very useful as a conversion factor. 14% means 14 grams of solute per 100 grams of solution. Parts per million, parts per billion, same thing, just the multiplier is different. Here you're multiplying by 1,000,000. This is abbreviated ppm. And if you look at the water quality report that comes to your house, they're going to list contaminants and stuff in parts per million and parts per billion, ppm and ppb. So it's just the ratio of the masses times a million or times a billion. So if we have something that's 15 parts per billion by mass, that means there are 15 grams of solute in a billion grams of solution. So anything that's parts per billion, very low concentration. You can also have parts by volume. So volume of solute divided by volume of solution, following the same pattern with the multiplication factors. So 22% ethanol by volume, 22 milliliters of ethanol in 100 milliliters of solution. What mass of sucrose in grams is contained in 355 milliliters, which would be 12 ounces, of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. Well, where do we even start on this? We've got 355 milliliters. We can start by just writing some stuff down. 355 milliliters. That obviously is a volume, right? Volume of what? Is that the volume of solute or solution? The volume of the solution. That could be useful. We have a density, 1.04 grams per milliliter. That's the density of the solution. That's just, I think I need a new stylus. Either that or a new hand. This is the chemist's abbreviation for solution. We get tired of writing that word. The 12 ounces we don't need. 15%, what does that mean? 15, 11.5. 11.5%, what does that mean? Yeah, 11.5 grams of solute. What is the solute? Sucrose. Per 100 grams of what? Solution. So now we've got some stuff here. What are we trying to find? Mass of sucrose in grams. Are you getting a clue as to how we can just put these together so the units work out? This is dimensional analysis. We want mass of sucrose. So we've got three different numbers here. We've got one with unit of milliliters, one with grams per milliliter, one with grams per gram. These are probably conversion factors. We should probably start with this guy. So we'll start with the 355 milliliters of solution. And I don't want milliliters of solution. I want to get to grams. So I'm looking at this, that has no milliliters in it. This has milliliters. This says that our solution is 1.04 grams of solution per milliliter of solution. So 1.04 grams of solution per 1 milliliter of solution. So then the milliliters of solution cancel out. So this is progress. And then we can use our percent, grams sucrose per 100 grams of solution, and put that in here so the units work out. Per 100 grams of solution. $3.55 times 1.04 times 11.5 divided by 100. 42.5. 42.5 grams of sucrose in a 12-ounce soda. That's a lot of sugar. Any questions? Pulling the numbers out, looking at the units, putting them together. There's no equation, it's just the units. Other ones are mole fraction and mole percent. Mole fraction has the symbol chi, it's a Greek letter X. The mole fraction of solute expresses the concentration as mole solute divided by total amount of solute and solvent in moles. So here N being the number of moles of solute divided by the total number of moles of solution. You can't really calculate those together because they're different, but you've got solvent and solute. So that's the mole fraction. You multiply that by 100 and you get the mole percent. You're going to need to be able to use these different concentration units. And one of the confusing things is remembering which one means what. And the names are descriptive. Most of them, it's something about the solute divided by something about the whole solution. What's one that's an exception? Molality. Molality gives us kilograms of solvent. But I think everything else is the amount of solution. So here's another example. A solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. Fun, fun, fun. Just sit down for a nice afternoon of calculating stuff, right? Molarity equals what? Moles of solute per liter of solution. We start with the one that should be easier. Well, what do we have here? They didn't give us moles of solute, right? Did they give us liters of solution? Not quite. They gave us milliliters, right? But we can convert milliliters to liters in our heads by now. So that's 0.355 liters. How are we going to find the moles? We need the molar mass. So they gave us the formula there. I'll calculate it for you. I should remember this, but there's lots of things I should remember, like my children's names. But one of them called me Michael the other day, so that was pretty funny. I'm like, really? Dad, I understand, but you're calling me your brother's name. Of course, now I probably did that calculation wrong. I'm getting 343.88. And speaking of children, they're calling me, and I'm going to ignore them. 12 times 12.01 plus 22 times 1.008 plus 11 times 16. Yeah, I didn't think that was quite right. Um, 342.3. Is that better? Anybody else do it? Yeah. Okay. So grams per mole. So there's the molar mass of sucrose. So we've got 50.4 grams. Hopefully this part is old hat by now. So we're going to put this together so the grams are in the bottom, they'll cancel out, and moles on top. And we got the 342.3. 50.4. I get 0.147. 0.147. I'm going to carry a couple extra digits there. Moles. That's the number of moles of sucrose. So that's what we're going to plug in down here. 0.14724 moles. Divide by 0.355. And this would be considered a final answer, so we should have 3 sig figs in that. I'm getting 0.415. Anybody else? Okay. Moles per liter. Okay, so that should be pretty straightforward. Mole fraction. What does mole fraction mean? The moles of solute, which would be N, divided by what? The solute plus the solvent, right? There's just no really fast way to write all that. Well, we just calculated moles of solute, right? So that's good. 0.14724 moles. And then on the bottom, we're going to have that same number for the moles of solute, plus, now we need the moles of solvent. They gave us the mass in kilograms of water. They gave us 0.332 kilograms. I'm going to write kilo as 10 to the third kilograms of water. And so if we multiply by the molar mass of water, upside down, it's moles per 18.02 grams. I've never done the sideways thing before. I don't think I'll do it again. Although it's fun looking at people with their heads tipped. 0.332 times 10 to the third divided by 18.02. Getting 18.42. Moles. Anybody else get the same number? 18.02. See, I should let's go, that would run 18.4240. I'm going to throw a couple extra sig figs in there to avoid some rounding problems over here. So that would be 18.4240. This guy has uncertainty in the third place, and so I wanted to make sure that I ended up with 3 here. Just because, but then when we go look, where is the uncertainty in that guy? This guy over here? How many significant figures should he have? 3, right? So there's uncertainty in the 10th place. So this is one where we got to be careful with our sig figs. So we've got 18.4240 plus 0.14724. That comes out to 18.57 stuff. That's going to have uncertainty in the 10th place, which gives it 3 significant figures. And that gets divided into this one on top, which has 3 significant figures. So we're going to have 3 significant figures in our answer, so that'll be cool. times 0.14724. That's a little number. The mole fraction then, throw it up here, is 7.93 times 10 to the negative third. There are no units on a mole fraction. The units cancel out. Is that a reasonable mole fraction? Could you have a mole fraction over 1? No, because the part can't be greater than the whole, right? So it's got to be less than 1. It's less than 1. It's small, but it is what it is. Molality. What's molality? Moles of solute per kilogram of solvent. Oh, nice. We already have those numbers. 0.14724 moles, 0.332 kilograms. 14724 divided by 0.332. So this comes out to be 0.443 moles per kilogram, which is also sometimes written as 0.443 lowercase m. I really don't like that because it looks like meters. See how this number is close to that number, but not the same. They're the same ballpark, though. Molarity and molality will be in the same region. They'll be close. What's the mole percent? Well, let's, we were just learning about these, and so we're a little fuzzy. What's percent? Parts per 100, right? So our general idea of percent is it's the part over the whole times 100. So mole percent must be moles. Moles of solute divided by moles of solution, which would be moles solvent plus solute, times 100. It's the mole fraction times 100. We already calculated the mole fraction. So it's the mole fraction times 100. That's a chi, not an x, in case you couldn't tell. So the mole fraction, 7.93 times 10 to the minus third times 100, 0.793%. One more, percent by mass. Again, the idea of the part divided by the whole, something about the solute divided by the whole solution, percent times 100, by mass, we're looking at the mass of the solute and the mass of the solution. Okay, what is the mass of the solute? 50.4 grams. What is the mass of the solution? Yeah, we have to add the mass of the solvent and the mass of the solute. They gave us the pieces, they didn't put them together for us. Because this is a big jigsaw puzzle. And one's in grams and one's in kilograms. So we have to be careful when we add those together. Since the numerator is in grams, let's do the denominator in grams as well. So 0.332 kilograms is 332 grams plus 50.4. So 50.4 plus 332 is 382.4 grams. Where's the uncertainty in that sum? The 2, the ones place. Because 0.332 kilograms is 332 grams. There's uncertainty in the ones place. 50.4 grams has uncertainty in the tenths place. So that would be the mass fraction, which we don't usually refer to, times 100 will get us the percent. So that is 13.2%. I see people do some really funny things in their labs when they calculate a percent. Because they'll do this and they'll multiply by 100, and then when they write it over here, they multiply by 100 again. It's probably the people that didn't show up that are doing that. I'm sure none of you would do that. You can't just throw in extra hundreds. If you want to do that, just throw extra $100 bills into my pocket as you leave today. That'd be good. Any questions? In order for you to be able to remember this for the rest of the week, for the final on Thursday, you're going to have to do some practice questions. And don't be intimidated by the different ways of quantifying the concentration, because the names are descriptive and the basic idea is the same for all of them. Here's another one. What's the molarity of a 10.5% by mass glucose solution? The density is 1.03 grams per milliliter. Let's pull numbers out. Worked before. What does 10.5% mean? Grams, 10.5 grams of glucose per 100 grams of solution. I'll have to watch the video and see if we can hear the squeaking. So that's useful. And then we've got a density, 1.03 grams per milliliter. That's grams of solution per milliliter of solution. We're trying to get the molarity. Molarity has units of what? Moles per liter. So we need to convert, because this is a concentration, it's just not the right units. So this is really what we're going to start with. Here we have no instance where we have a number with a single unit. They both are per. So then we have to pick, are we going to do this one or this one? This is the one that's more closely related to what we're trying to find. We're trying to find moles per liter. This is grams per 100 grams. But using this number, we can convert grams of solution to milliliters of solution, and then it's a little baby step to liters of solution. Can we convert grams of glucose to moles of glucose? Sure we can. We just need the molar mass. So the molar mass, the formula is given. It's 6 times 12.01 plus 12 times 1.008 plus 6 times 16. So the molar mass is 180.2 grams per mole. So now we can put these together. 10.5 grams of glucose. Do you absolutely have to write glucose in there? No, you don't. But if you find yourself getting the wrong answer, then you probably should. Because it's just good to be clear on what you're dealing with. So I want to have grams of solution on the top to cancel out, and I see that I've got that in here, so that's going to be 1.03 grams of solution per milliliter of solution. And then I could go milliliters and liters. So I got those grams gone, and I've got milliliters gone, and now I've gotten my denominator switched over, and now I will use my molar mass. I want moles on top. I want to get rid of the grams, 180.2. This gram of glucose cancels that gram of glucose. So we got 10.5 over 100 times 1.03 divided by 10 to the minus third divided by 180.2. And this should end up with 3 sig figs, so I'm getting 0.600 moles per liter. Any questions?